All right, so we're going to try something a little bit different. I didn't really like the way I was using OneNote, so I'm going to try to change it because I think there's something unsatisfying when everything's already written down. So what I'll do is I'll give you guys my hand-copied notes. We'll try it this time, and if you guys like it better, cool, we'll do it this way. If not, then maybe we'll adjust and find some mixture between what I've been doing in the past and what we do today. All right. So one of the other things that I want to do is the next couple chapters are actually I think a little bit challenging and in fact super important. So I'm going to go through them at a little bit of a slower pace. So that was part of the reason why I didn't want to get into permutations and combinations at the last lecture, because I do think it's worth sort of focusing in on and thinking about in a little bit more detail. All right. So we have two basic concepts that we're going to go over. One of them is permutations, and the other will be combinations. And they both sort of derive, well, at least we can say permutations derives from this idea of like counting the number of ways things can happen using groups. It comes from the product rule that we sort of mentioned earlier. Okay. And then, actually I drew this area the wrong way. Combinations can be sort of a simplification of permutations. Okay. So when we were talking about the product rule, sort of the canonical problem we had was, okay, you're going to pick two doctors. All right. So I forgot, maybe one's a dietitian, the other's a PT, right? So this can be your PT and this can be your dietitian. And maybe there are 5 possible options to pick from for the PT and 2 possible options to pick from for the dietitian. And so the total number of options is just 5 times 2. So you have 10 total options. Okay. All right. So this was the product rule that we sort of had before. Permutations are sort of like an extension of this. But instead of picking objects or elements from 2 separate groups, we're actually picking them from the same group. And then we don't sort of refresh what we're picking from. So, the canonical problem is, all right, I have, a bunch of balls inside of a bag, and I'm going to pull them out. All right, and maybe, they're numbered with letters, right? A, B, C, D, E. Okay. So here I have 5 balls in the bag, and I'm going to pick 3 out. Okay. And so we can think about it as, okay, there's one draw here, and we're going to put a letter, and it's going to be A, B, C, D, or E. We're going to pick another draw, and then a third draw. And depending on what I picked in the first one, it's going to reduce my options for the second and third, right? So maybe I picked, B for this first one. So in the second draw, my options are A, C, D, and E. And let's say I pick E. Now my options are A, C, and D. And let's say I pick A. Okay. The product rule is actually still applying in some ways, right? So when we're doing a permutation and we're trying to see how many different ways we can pick out 3 of 5 objects where we care about the order, the reason why we're still using this product rule is because we're saying, hey, in this first draw we had 5 options. In the second draw, we had 4 options, and in the third draw, we had 3 options. Right? And so the permutation of how many different ways can I pick out 3 letters out of 5 lettered balls is just given by 5 times 4 times 3. Okay, so it's not so bad. there's a generalization to this equation, right? Which is we normally define our problems by two parameters, n and k. Okay, so n is the total number of objects that we're selecting from, and k is the number that we're actually pulling out. And so we'll normally denote the number of permutations as p k sub n, right? All right. The equation for calculating this is just given by, what is it? I think you want n factorial divided by n minus k factorial. And we can actually see that sort of show up here. Okay? So in this problem, we were trying to calculate p3 comma 5. And we saw that was 5 times 4 times 3. Well, if we multiply the top and bottom by, what? 2 factorial, I think? Yeah, 2 factorial. Then we actually end up with 5 times 4 times 3 times 2 times 1 over 2 times 1, which is just given by 5 factorial over 5 minus 3 factorial. Okay. And so that's kind of where this equation comes from. It's just a generalization that we have. Alrighty. So there's more or less how we calculate permutations. It's not, as this is stated, it's not particularly exciting, I don't think. I don't know how many problems you can have, but they tend to be pretty obvious when it's a permutation problem. So you'll have stuff like a baseball team has 15 players. How many 9-player lineups can you pick? Or can be generated? All right, and this is actually a pretty straightforward application of permutations because we know each person will be assigned a position, and we have 9 positions. And so in some sense, the order matters in that each person can only play one position, right? And so it's not just, okay, what are the 9 players that are going to be playing on the field, but where do we actually stick them? So in that case, we're just calculating P915. All right, so we'll take the factorial of 15 divided by the factorial of 15 minus 9. Okay, and this will give us the total number of lineups that we can actually calculate. We should be kind of careful because this number gets really big, right? These factorials grow large. All right, so I don't even know. Let's see. Let's calculate this. So 15 factorial. I don't know, some ungodly huge number, right? So nobody actually calculates the factorial. Usually what we do when we're doing this calculation, we just know that we're going to end up canceling some of the multiplications, right? So again, we're going to have 15 times 14 times 13, ... all the way times 2 times 1. And on the bottom, we're going to have, what's on the bottom? 6 times 7, oh no. 6 times 5 times 4 times 3 times 2 times 1. And so we're going to end up canceling a bunch of stuff on the top and bottom. And we're just going to be left with 15 times 14 times 13, ... all the way to times 7. Right? So just be careful if you're using some sort of combination or permutation calculator, and you're trying to do it, let's say in Excel you actually tried implementing this equation here. This is a bad idea, okay? Don't actually, try to implement that directly where you say, factorial n divided by factorial n minus whatever, okay? Excel at some point just starts barking, right? So this is also a really common problem when you're computing small probabilities. So that's just something to be aware of. Things get a little bit more interesting when we start working with combinations, all right? So in combinations, we're still drawing objects, but now the order doesn't matter, okay? Okay, so we might still have our bag of balls, right? Or in fact, I think the example that I use is sort of lottery balls. And we're going to draw a ball out one at a time. And it actually doesn't matter what order the balls come out in. So if you guys ever see lottery, what they end up doing is after they draw the balls, they actually sort them, okay, from smallest to largest. So it doesn't matter what order they come in. And so if we want to count the number of combinations, we're going to end up using a slightly different equation, right? Ck of n. And sometimes it's written this way. And it's given by n factorial over k factorial n minus k factorial. Okay. And again, we sort of mentioned it the last time. Folks usually call this n choose k, and I never really understood that language. So in my head, I just put from before that, and that makes a little bit more sense to me. Okay, so I think it's actually worth understanding where this equation comes from, at least intuitively. Right. So one of the example problems that they have in the book and that I sort of have in the notes is we have a bunch of students who are selected for, let's say, some student government board for their College of Engineering. And they take one student from each major. And so, we'll just call these students A, B, C, D, E, F, G, right? Okay, so these are the 7 students representing the 7 majors in their college, right? And so they're part of some, student body. Of those, we're going to pick 3 who will serve as some sort of leadership, right? Now, Now, typically, let's say we are doing the permutation problem, and we'd say, okay, one is going to be the president of the student body board, the other will be vice president, and the last one will be treasurer or maybe secretary, okay? So if we had assigned roles, in that case, we'd be dealing with a permutation problem, okay? And so the number of permutations we could have, let's say again, 3 roles out of 7 students would be P3, 7. Okay. And so we could actually calculate that out pretty quickly, maybe, I don't know. It would just be 7 factorial divided by 7 minus 3 factorial. And again, nobody actually calculates the factorials. If you want to know what it is, it's 7 times 6 times 5, all right? And so, I don't even know what that is. 210. Yeah. Is it in there? Yeah, it is. All right. 210. Okay. So let's pretend that, we have some sort of communist student board, and they decide, hey, nobody's president, nobody's vice president, or treasurer. We all want to look good on our resume, so we're just going to be like directors of the student board. That way, all three of us can put director, right? So this, we have this mini junta that ends up getting created, right? So all the assigned roles are equivalent. Okay? So it doesn't matter who's president, vice president, or treasurer. Okay? So one way that we can sort of think about how we would calculate that is we can pick one instance of a permutation, right? So let's say A, C, and G were selected to be to have some sort of role, okay, in this leadership board. Now, there's a whole bunch of different ways that could happen. All right, we could have A be president, C be vice president, and G be the treasurer, or we could start mixing them up. So let's sort of, I'll put this in some sort of order. All right, maybe A is president, we have G as vice president, and C as treasurer. We could also flip it around and have C being the president, and then A and G. And of course, they could flip their roles. And finally, we could have G be president and C and A be vice president or treasurer. Okay? And so what we have here are 6 total options. For how this could happen, right? Sorry, I had it on vibrate, but that was very distracting. We have 6 total options for how we could have created permutations with A, C, and G. Okay? But what we're saying is we don't actually care because now we've made them a junta where they're all equal, right? So we're going to say these 6 options are equivalent to one combination. So these are all the permutations. All right. Well, this guy is the combination. Okay. And this gives us some intuition where if we want to talk about how many combinations we can pick, right? For every 6 permutations, we end up with one combination, right? And the 6 isn't coming from nowhere. It's actually coming from 3 times 2 times 1, right? Which is the number of ways that you can sort of reorder these guys, right? So if we want to find some sort of relationship between the combinations and permutations, we basically get rid of this reordering. Okay, so we're going to try to factor it out. Right? And so that relationship sort of leads us to the following equation, where the number of permutations, right, or we can do it the other way. The number of combinations is equal to the number of permutations divided by k factorial. Oh, no, not divided. Which way is it? Yeah, that's right. Okay, I always like it better this way. All right. Yeah, the number of permutations is some scaling times the number of combinations. All right. But if you want to reverse that relationship, we can write it this way. Okay. And so again, the basic idea is we'll always have more permutations than combinations. All right, so it's sort of gives us some sort of intuition of where the equation for the combinations work or come from. We can expand out this pkn, right? We already know that it's n factorial over n minus k factorial, and now we're just dividing again by the k factorial. Okay, so this gives us some sort of intuition of where we're getting the number of combinations. Rock and roll, going a little faster than I thought. All right, so let's actually, what I want to do, and what you'll see, I think, for the rest of this packet, is me going through a bunch of different examples, okay? And I think these examples will help you sort of understand the problems in the book and how to go about solving them. All right. So the first example I want to do is a 5-ball lottery, okay, where each ball is a number between 1 to 60. Right. And so what we're going to do is we want to first ask how many different combinations of like a winning lottery draw can there be? Okay. And so this is a pretty straightforward problem. So all we want to calculate is the combinations of 5, 60. So 60, choose 5. Okay, so out of 60 numbers, right? So we have this whole thing of balls. 1, 2, 3, 4. We're going to choose 5 out of that. Okay. So again, this is sort of the classic example of don't try to take 60 factorial. That's just a really bad idea. Okay. So there's the number we want to calculate. All right, and this will give us the total number of combinations of ball draws that there could possibly ever be. All right. So if you make the cancellation in the factorial between this top and bottom, all right, what you're left with is 60 times 59 times 58 times 57 times 56 all over 5 times 4 times 3 times 2 times 1. Okay. If you bust out your calculator, you can follow along with the equations. We end up with 546,000, or no, 5 million draws about. Okay. All right. So that means if there's a 5-ball lotto, right? There's about 5 million different combinations that could come out of that. All right. So if I go play, I go to the gas station and I buy a $1 ticket, my odds of winning, right, is just one of those draws. All right. So that's usually the question we want to ask is like, all right, what's the probability of winning lotto? Okay. And it's just the number of, whoa, all right. So the number of ways of matching all numbers divided by the total number of ways that we can draw 5 numbers. Now, there's only one way we can match all 5 numbers, which is my 5 numbers are the 5 numbers that get picked. So if we want to calculate that probability of winning, it's just 1 over 5.4 million, right? Okay. So what this tells you, later on we'll get to this when we start doing expected earnings or expected reward, doesn't really make sense to play lotto unless the expected reward for the lottery is more than $5.4 million, okay? Or else on average you're going to lose money. Somebody actually went through all the calculations for the Powerball game a few years back. And how many of you guys have ever played Powerball actually? No? Okay. So Powerball is an interesting form of lottery. And what they do is basically it starts off as a standard lottery. And if nobody wins, they take all the money that they had earned from people buying tickets and they put it to the next lottery. And if nobody wins again, they take that money and put it to the next lottery. And they keep doing that over and over and over again until somebody wins. And that's why you're able to see these Powerball drawings that are like $1 billion, okay? Because nobody had won the Powerball lottery for like 10 drawings in a row. And so the pool just keeps getting bigger and bigger and bigger. Right? And so there are times actually where the winnings that you could get from playing Powerball are so large that it actually makes it worth it to buy tickets, right? Like on average, you're gonna, well, not really on average, but in theory, on average, you'll end up making more money than you'd spend on a lotto ticket, okay? There's actually some very famous cases where people realized this and they had state Powerball games and people bought every single lottery ticket, okay? Because they knew, hey, if I buy something like 80% of the lottery tickets, I'm gonna get, I'm almost guaranteed to win and I'll make 20% on that money that I invested. So I'll post some stuff on it. It's really, really neat. I don't know. I think it's fun. Okay, so we have the odds now of winning lotto, like full out, you got all 5 numbers. All right. Things get a little bit weird and complicated when you ask the question of like, what are the odds of winning 2? Or only matching, 2 balls or 3 balls, right? Or 1 ball, right? It's not like the number of ways you can do that is actually a lot more than, well, the equation's a little bit tricky. Let's just say it didn't sort of pop out at me the first time I learned it, okay? And so that's kind of what I want to go through. So we're still going to do the 5-ball lottery. All right, with numbers 1 to 60. And the question we're going to ask is, what's the probability of matching 1, 2, 3, 4, 5, and, well, we already did 5. 1, 2, 3, or 4 numbers. Okay. So the way we're going to start by doing this is we're going to define the event. Okay. So and here I'm going to define this event M of I. Okay. Where M of I is the event of matching I balls. Okay, so if M1 is matching 1 ball, M2 is matching 2 balls, right? Okay. So if we want to talk about what is the probability of M2, all right, what we need to do is count the number of ways we can match 2 balls divided by the total number of ways we can draw 5 balls, okay? All right. Okay. So the reason why I want to say I don't think this is as straightforward as you might think, or I thought, is my first intuition when I learned probability is to say, well, the number of ways to match 2 balls is given by 5. Oh, did I write that backwards? No, 5 choose 2? Yeah, 5 choose 2. Why does that feel backwards? That notation. Yeah, it is backwards. Smaller number goes first. Okay. 5 choose 2. Okay. That was always my first thought, right? Because you have 5 numbers, and you think, oh, I'm going to match 2 of them. Well, what we really want to think about, right, is if you match 2 numbers out of 5, that means you're not matching 3 numbers out of the remaining 55 numbers that could have been drawn. Okay? So the missing part of this equation for this case would be C55, C3, comma 55. Okay, so let's sort of break this down again. All right, so I've drawn 5 numbers. Okay? Of those 5 numbers, 2 are going to match. Okay, so again, we can come up with a silly example. One, 2, 50. Let's say these are my 5 numbers. Okay, and I told you 2 are going to match. The number of ways that 2 numbers can match, it could be maybe 10 and 20 match, 10 and 36 match, 10 and 37 match, right? Or maybe it's 20 and 36, 20 and 37, 20 and 50, right? And so we can go through all the different ways that 2 of the numbers are selected to match. Okay? But I still require 3 numbers do not match at all. Okay? So what that means is, instead of drawing 3 numbers out of the 60, right? What I'm drawing are 3 more numbers. So I have 2 numbers that match. I need to pick 3 numbers that don't match. And those 3 numbers have to come from the 55 numbers not included here, right? So there are 60 numbers. 5 of them have to be removed because those are my numbers. Okay? And so the 3 remaining numbers that get drawn are accounted for here. So that's the kind of way you want to think about it, right? Which is, okay, 2 numbers of my 5 are going to match. 3 numbers are not going to match. And those have to come from the set of numbers that I don't have. Okay. Now, we can generalize this equation, at least for the 5-ball case, right? So it's going to be I, which is the number of balls we're matching. And then we're going to be drawing 5 minus I balls out of 55. Okay. So using this equation, right, we can start calculating all the probabilities. Right? So in the notes, you see I made a little table for the different options of matching 1, 2, 3, 4, or 5 balls. Okay. And so we have our different events. Okay. Any of you have your probability book? Do you have your book? Can I take a look at it? I feel really unsettled that I have the notation. Okay. Yeah, so I'll, in your mind, correct the notes, right? I've mixed my cane and the notes here. Okay. So we can start calculating all these values. So 5 choose 1, or 1 5 choose 1 is given, we have 5 ways that we can do that. 5 choose 2 is 10. 5 choose 3 is 10. 5 choose 4 is 5. And then 5 choose 5 is 1, right? So that, again, we saw this before. This is matching all the numbers. Okay. So this next column is the number of ways that we can not match the remaining numbers, right? So if we only match 1, the number of ways we can not match 4 numbers is actually quite large. There's about 300,000 different ways. All right, so if we don't match 3 numbers, there's about 1,400 different ways, 55 and then 1. And what we want to do is take the product of these guys, okay? And so this final number this gives us the number of ways to match I numbers, or match eyeballs, right? Okay. So you can go through this multiplication. I'm just multiplying the columns by each other. Right. And so what this tells us is if we want to know the probability of matching 3 balls, we just sort of take the value in this column and divide it by the total number of ways that we can draw 5 balls. Right, so right. So this gives us some sort of probability. Okay, so if you ever want to figure out what your chances of winning lotto look like, you can go through this math. It's pretty disheartening, right? Yeah. Okay, so the remainder of the problems are, I think, very similar to ones that you'll see in the book and probably that you'll get in the exam, right? So I have one problem with baseball, and then the rest are like, how do you calculate the probabilities for different poker hands? And so what I want to do is go through them, and I'm hoping that by you guys seeing a bunch of these examples, it will kind of get drilled into your head on how to do them. All right. What you're going to find is that most of the problems are sort of this combination of permutations and combinations using this product rule. Okay. Something like that. Okay. All right, so let's sort of work through a couple and you'll see sort of what I mean. All right. All right. So let's say we have some baseball team. And there's 15 players, 9 of which are going to sort of be on the starting lineup. Of the 15, we'll say 5 of them are left-handed. Which I actually think is kind of high. Anybody know the pervasiveness of left-handedness? 10%? Yeah. Well, this is actually a lefty-dominant team. Okay, so there's the basic info. All right, and so what I decided as coach, because I'm left-handed, I don't know, or maybe I'm right-handed, who knows? I want to reserve certain positions for my left-handed players, okay? And so my question will be, if I reserve 2 left-handed players to play outfield. And one left-handed player to play infield. How many different lineups can I have? Okay. So the way I want to solve this is not to jump directly to the permutations. At least for me, I think of it first in terms of combinations, and then I add in the permutation part afterwards. Okay. So the way I think about it is I'm going to break it up into two parts. First, I'll think about what's happening in the outfield, and then the infield. All right. So in the outfield, I'm going to put two players there. Okay? And so that means, or two left-handed players there. That means I have to pick two of my 5 left-handed players. All right? And so that's where I get 5 choose 2. Okay? So from 5 left-handed players, I'm going to pick 2 to show up in the outfield. Now, I have one more outfielding position. So for those of you who don't know baseball, outfield normally has 3 players. Okay? And so that means that remaining player is going to come from one of my left-handed players. If I have a team of 15, where 5 are left-handed, then we're going to have 10 right-handed players. So I want to pick, of those 10 players, I'm going to pick one of them to play in the outfield. So now let's focus in on the infield. The infield has 6 positions, right? And we're going to start by assigning one of those positions to our left-handed player. Now in this case, and the notes are wrong. How many, after we've assigned 2 left-handed players to the outfield, how many left-handed players do we have left? 3, yeah. So we're going to pick one of those 3 players to play infield. Now, in terms of our right-handed players, we started off with 10. We chose 1 to play outfield. Okay. We have 9 players left who are right-handed. Okay. And they're going to be assigned to the remaining infield positions. So I told you before, normally infield has 6, outfield has 3. All right. We've assigned one of those positions to a left-handed player. And so what we have left are 5 positions for right-handed players. Okay. Now, this isn't a lineup because I haven't actually assigned which position to which player. Okay? This is sort of figuring out just what players are going to be in the infield, what players are going to be in the outfield. I still need to assign them actual roles. Okay. All right. So this is more like the combinations. Okay. What we really want are the permutations or the specific lineups. And so, at least for me, the way I think about it all right, so again, we'll divide it up. Outfield has 3. Infield has 6. Okay. So for these 3 players, I can sort of rotate them around. Left field, center field, right field. All right. This was kind of like the vice president, president, and treasurer positions. Okay. So the number of ways that I can reorganize these 3 players to play 3 different positions is given by 3 factorial. So what I end up doing is I take the total number of combinations of players that I can have in the outfield, and then I look at how many different ways I can assign them to those 3 positions. And so all we need to do is multiply times 3 factorial. So in the same way, we can actually figure out the number of lineups in the infield. All right, so if we have 6 players playing in the infield, we can assign them to different positions, 6 factorial ways. Okay. All right. And so that's more or less how you calculate the total number of lineups. Right? So if you want, you go to some calculator and you calculate all these numbers. I'm sure it's actually quite large. Okay. So let's see what's going on here. We actually have 2 things happening, or 2 or 3 things happening. All right. First, we're applying the product rule, right? So the number of combinations for outfield times the number of combinations for infield. Then we're applying basically a combination or a permutation, right here. And so there are 2 different rules that we're actually applying in the process of solving this problem. Okay. So this is going to be really common throughout the homework assignments. Okay. So, all right. With that, what we're going to do is, I found this to be actually really helpful when I learned combinations and permutations. We're going to go through all the, yes, sir.
Say for that last example, if you did the infield first, like 10 choose 5, and then 5 choose 1, and then for the outfield you like subtracted.
Yeah, you'll get the same answer.
That's pretty good.
Yeah, and we kind of see the where this is coming from up above. So take a look at this column right here. All right. So we're missing the case where I equals 0. Okay, but you can imagine if I were to put an I equals 0 row, the ci comma 5 would be 1. So in fact, it's symmetric, right? And so that's what it ends up happening. So whether you're doing the outfield first and then the infield, it doesn't matter because there's sort of the symmetry to the problem. Yeah, so you're either subtracting players on one side and adding them to the other, or vice versa. Yeah, so that's why you should get the exact same answer. Yes, sir.
So if like all these combinations of things that we can't really do in Excel because it'll break our computers.
Yeah.
How do we calculate that?
So it's, well, let's actually. So I always do combination calculator, right, in Google. That's done. But there actually might be. Yeah, so there is a combine function. All right, so let's go ahead and check that out. I'm surprised that there is. Let's see how it works. Yeah. So actually, it is worth it. You might as well just like have a sheet in Excel for combinations and permutations, and you give it n and k, and it gives you the answer. Okay, so we can. Let's go ahead and do that. All right, so you can do n, oops, k, yeah, so you might as well just keep this, something like this in here. All right, so let's see. I think the function was combine. Yeah. Oops. Ooh, wrong order. Yeah, there we go. Okay, that sounds about right. So what is permutations? Yeah, cool. There you go. Okay. So, if somebody reminds me, I can put this spreadsheet up on the modules. That way, if you didn't quite catch what functions I typed in, then you'll have it, and you can just copy and paste them over to your Excel sheet. Right. So yeah. Okay, so now my recommendation is have this spreadsheet handy and ready. You're done. Or you can be like me and Google combination calculator every single time you do a problem. Yes, sir.
A lot of scientific calculators.
Oh, they do it now?
Yeah, they have like this one that has the PRD button. So you do like 10, you get the PRD, you have your permutation, your combinations that you choose.
Oh, cool.
And then you do it.
Awesome. Okay, he has a TI, so if you have a TI, it probably has that exact same functionality.
36x per horizon 2.
Yeah, so I'm sure the graphings do as well. But yeah, so you do whatever you need to do to get it calculated quickly. All right, so if you want to just have this Excel spreadsheet ready, hey, by all means. Yeah. Okay, so let's sort of, I think examples are always key here because I hate combinations and permutations. All right. So what I want to do is go through poker hands, okay? So we're going to do 5-card poker hands. So just in case not everybody knows, so a standard deck has 52 cards. Okay, those cards are divided up by rank and suit. Okay, so rank is like 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, Ace. Okay, so we have 13 different ranks. And I had to look, I didn't know it was called a rank. I thought that was kind of neat. So we have 13 different ranks, and we have 4 different suits, which are hearts, clubs, spades, diamonds. Yeah, 4 different suits. Okay. All right. So we're not going to play a complicated game of poker. There are lots of different poker variations. Basically, we're going to ask, if you're to draw 5 random cards from the deck, what is the probability you get a pair, or maybe 2 pairs, or a full house, or a straight flush, or a royal flush? Okay, and we're going to go through all those different examples. And if we can count the number of ways we can get each one of those hands, then we can calculate the probability of getting that hand. Okay. So one of the first questions that we should, and actually I'll just do this now. For those of you who don't know poker, there's like an ordering of hands from highest to lowest. The highest is a royal flush. Okay. That's where you have a 10, Jack, Queen, King, and Ace, and they're all the same suit. So they're all hearts or diamonds or whatnot. I think after that is something called a straight flush. Here, all the cards are the same suit again, but instead of starting off with the number 10 and going 10, Jack, Queen, King, it could start with any number. So it might be, or any sequence. It could be 5, 6, 7, 8, 9, but they all have to be the same suit. What's after that? I think 4 of a kind? Yeah. After that is 4 of a kind. Okay, so that would be like a 6, 6, 6, 6, and then maybe a jack, right? I think after that is a full house. Oh, what is it?
Full house is above 4.
Oh, it is. Okay. Hold on. I have it here. 4 of a kind. Yeah. No, 4 of a kind. Full house is, yeah, and then it goes full house. Okay. So a full house is when you have, what is it? 3 of a kind and a pair. So you'll have something like, I don't know, Jack, 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 and then maybe an 8 and an 8. After full house, flush. Yeah, we have a flush, where all the cards, they could be any number. But they all have to have the same suit. Okay, so they all have to be diamonds or all have to be clubs. After a flush, we have a straight, which again, it's just a sequence of cards, an ordered sequence, but they can be different suits, or they are different suits. They have to be. Okay, because if they're all the same suit, then you'd have a straight flush. Okay, so after a straight, we have 3 of a kind, which is, 5, 5, 5, Jack, 9. Okay. And again, 3 of a kind. What's after that? 2 pair. So that would be like 5, 5, and ace, ace. And then we have some random card. And then we have 1 pair. Right, and then nothing, right? Okay, so what we're going to do is go through and count the number of ways we can get these different hands. Okay? And in fact, I'm going to go a little bit backwards. Maybe? I don't know. Nah, actually, I'll go the right way. I'll start from the bottom. So normally people start from the bottom up. So that's what I'll do. But I'm going to skip a couple cases. All right, so for this first case, we're going to do 1 pair. Okay, so we want to count the number of ways that you can get 1 pair. All right, so the way you want to think about it is like that baseball problem with left-handed and right-handed players. Okay, we have, or maybe even the lotto balls, right? We have 5 cards that we're getting. Okay. Of those cards, actually no, sorry. We have 5 cards that we're getting. No, delete that, sorry. Okay, so when we have a pair, that means of our 5 cards, 2 of them are the same, 3 of them are just random and different. Okay, so we have to pick 1 rank of the 13 possible ranks, okay, that we're going to have a pair of. Okay, so maybe it's aces, we have a pair of aces, or maybe it's a pair of 2s or a pair of jacks. Okay, and so what we're going to do is out of the 13 possible ranks, 1 of them, we're going to pick 1 number to be a pair. All right, so now we've picked that number, let's say it's 10. Okay, we have to figure out how many different ways can I get 2 10s. Okay, and the number of combinations comes from the number of suits. So there are 4 total suits or 4 10s. We want to pick 2 of those different 10s. Right, so maybe it's clubs and diamonds, or diamonds and spades, or spades and clubs. Okay, and so that's where we get 4 choose 2. Okay. So this section right here, sort of, I'm going to use this very rough, right? This defines the number of pairs that we can get. Okay, so now that we've defined the number of pairs, we have to make sure that the rest of the cards are nothing, right? We don't want to get another of this. Whatever this pair was, we don't want to get another one like it, right? So we need to make sure we don't end up with 3 of a kind, 4 of a kind, or 5 of a kind. Okay. We know we can't end up with a flush because we have 2 different suits for that pair that we're getting. Okay. All right. So what we're going to do is choose 3 more cards. Okay. Now those 3 cards, we can choose from any of the remaining ranks. So before we had 13 ranks and we chose 1 rank to make a pair. All right. So that means we have 12 ranks remaining. where we can choose 3 different ones. And we do this because we don't want to come up with another pair, right? And we subtracted 1 so that we don't end up with 3 of a kind here. So I'm going to pick 3 different ranks, right? And it can't be, repeated. So that's why we're doing 12 choose 3. All right, so each of those 3 cards now have to be assigned a suit. Okay. So for the first card, there are 4 options for the suit, and we're going to pick 1. For the second card, we have 4 options for the suit, and we're going to pick 1. And for the third card, we have 4 options, and we're going to choose 1. Okay. So if you want to sort of think about it, these red ones sort of correspond to the 5 and 5, right? So maybe we get 5 of hearts and 5 of diamonds, right? Well, these guys over here are all the combinations we can get 3 different cards. They can't be pairs. And so that's what we have here. Actually, this. So if you end up calculating this out, it's some huge number. Oh, it's some gigantic number, okay? So if we want to know the probability of getting a pair, it's this big number. Oops. Divided by the total number of ways that we can choose 5 cards. Okay. In our case, that's just 52 choose 5, which is about, what is that, 2,598,960 different ways. Okay. So if we want to know what that probability is, it's about 42%. Okay. So if somebody draws 5 cards, what this is telling you is you have a pretty good chance of drawing a pair. Right. Where that pair is, whether it's high or low, is a whole nother story. But this gives you an idea of how common a pair is, right? So this is why a pair is basically meaningless in poker and why it's the lowest hand. Right. Okay, so let's think about 2 pairs. And we're going to go through this same sort of process. Okay? So if we have 2 pairs, what we're doing is, of the 13 different ranks that we have, we're going to choose 2 numbers that we can pair up. So that's where we get 13 choose 2. Still have class. So again, 13 cards, different ranks. 2 of them we're going to choose to be a pair. Maybe it's a pair of 5s and a pair of 6s, or a pair of 10s and a pair of jacks, right? But we've established 2 ranks. Okay. Now for the first pair, again, we're going to do 4 choose 2, which is we're going to assign suits to the pair. So 2 cards, right? They're going to pick out of 4 suits, right? Likewise, because we have 2 pairs, we're going to repeat that again. So this for the first pair, the suit for the first pair. There's the suit for the second pair. After that, so we've drawn 4 cards and we have 2 pairs. We have 1 more card that we need to draw. All right. It can't be the same rank as the first 4 cards we drew. Right? So it has to be a different rank. So now instead of doing 13 choose some number, we're actually going to do 11 choose 1. Okay. So of the 11 other ranks, right, or numbered cards, we're going to pick 1. Okay? And that 1 card can be of any suit. And for that reason, we have a 14 choose 2. All right. So the number of ways that this can happen is about 120,000 ways. And this is the part that I find so interesting, is the drop in probability, right? So from one hand to the next, the drop in probability is a factor of 10, right? Which is like kind of crazy to me. Okay. All right, 3 of a kind is pretty similar to a pair, right? So we're still going to pick one number of the 13. Okay. And when we pick the suits of those 3 cards, we're just doing a 4 choose 3. We have 2 more cards to pick after we've picked our 3. So we're going to do a 12 choose 2, right? So we're choosing 2 more cards. They can't be the same, right? Or else that would give us a pair. And they have to be different from the 3 of a kind we selected. All right. So after that, we have to assign each one of those sort of extra cards, right, or meaningless cards a suit. So we have 4 choose 1, 4 choose 1 for each suit. So again, this will be like 5, 5, 5, right? And maybe this is a heart, that's a diamond, and that's a spade. And this could be 6, 10, and ace, right? And it could be anything for all we care. Oh, 2. Yeah, there we go. Yeah. Okay, 3 of a kind. The other guys more or less work the same way, okay? So what I want to do is I'm going to calculate a royal flush, which is actually really straightforward. And then we'll do the straight flush. Okay? So let's think about what a royal flush is. Okay, so a royal flush again has to start with 10. Go 10, jack, queen, king, ace. All right. The only choice that we have is the suit. Okay? And so for that reason, the number of ways that we can get a royal flush is 4. Okay? If you want to go through that, that's just what? 4 factorial over, what is it? Okay, 1 factorial, 4 minus 1 factorial. Okay, so you end up with 4 times 3 times 2 times 1 divided by 1 times 3 times 2 times 1. 4. Okay, so there are 4 ways to get a royal flush. Okay, so why did I jump to the end? It's because if we want to calculate a straight flush, that's basically, again, a sequence of numbers in order, all the same suit. Okay, so that would be like 5, 6, 7, 8, 9, and they're all clubs. I can't draw a club at all. Okay, I'll just say clubs. Okay, so here what we can do is we can pick the suit and we can kind of pick the starting number, right? Like, do we start at 5? Do we start at 2? Do we start at 9? Now there's only one number that we can't start at, which is 10. Okay, because if we started at 10, we'd have a royal flush. Okay.
Can you start at jack, queen, king?
No, because you don't. Oh, sorry. You can't wrap around, right? So, yeah, you can't wrap around. So basically, the highest number that you can start with is a 9. Okay. So that means you can start with an ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8. Did I miss a number? Or 9. Is that right? 2, 3, 4, 5, 6, 7, 8.
You
9.
started with ace the first time. I think that's
No, I want to start with. You can start with an ace. You can go ace 2, 3, 4, 5. 6. Okay, so actually there's another mistake in these notes, so just be aware. Okay, so the first card that you could start with could be an ace through a 9. Okay, so. Yeah, so you have 9 options of which card to start with. Okay, so that's why first we're going to choose our starting card. Okay. And we have 9 options to choose from. Right, that 10th option is starting with the 10, and that would be, again, a royal flush, so we can't do that. Or actually, no. I'll take it back. Here, now I understand what I did. Okay, yeah. It works out to be the same. All right, so we can, any straight, we can start with ace through 10. All right, and we can pick the suit. Okay? Now we want to remove the option of getting a royal flush, so we can subtract off 4, choose 1. Okay. Or we could have just said 9, choose 1. Same answer. Right? Okay. So take a look at the remaining ones. I think the more interesting ones are the, what was it? Full house is pretty cool, and a flush, I don't know, I think it's a little bit interesting. So definitely take a look at the full house and make sure that you can calculate it on your own. If you can calculate it on your own, then you're doing pretty good, I think. All right, thanks guys. Have a good one. If I haven't posted the videos yet, somebody please put a note like, hey, post the videos.